Actually, Guhesh gave a nice series of lectures on quiver subtraction last year, but the idea was to make it to this topic, which Guhesh has been working on, and we didn't. So now we're going to finally get to that. So it's going to be not anymore just quiver subtraction for slices along strata, but rather we're going to take a variety and form another. So we're going to take a modular space, take Coulomb branch, and take another quotient of it, right?
That's right. Yeah.
And subtract that way. Okay, so thank you, Guhesh. Can begin.
Thank you. So as Trevor said, the variety of this technique, quotient quick subtraction, which is a technique which allows you to take a Coulomb branch and compute a further quotient by some group. And I'll explain how we do this. This is possibly slightly strange if you're a mathematician because you think of hypercalic quotients as being associated with fixed branches. But nevertheless, this technique is kind of dual to the hypercalic quotient you already know and like. Okay. Well, okay, so am I just reinventing the wheel? No, because there are some advantages that we have with Coulomb branches, which are interesting. One is that we have constructions for exceptional Milverton orbits, which you do not have with expansion.
Well, what did you say was weird about doing hypercalic quotient from the mathematical point of view?
Oh, I'm not sure. Is it weird?
No, I don't think so.
Okay. Then it's not.
The only thing maybe one could say is that a lot of us are often thinking about it in terms of complex algebraic geometry instead, but it's just a different point of view, I guess. Most of the varieties in question have this hypercalic structure, so you can think about it that way, or you can think about it as the underlying complex structure.
Maybe that was just I've always seen the hypercalic quotient associated with Higgs branches quite frequently.
Yeah, exactly. The point is that you use hypercalic quotient to construct Higgs branches, but I guess there's no reason why once you have a Higgs or a Coulomb branch, you wouldn't want to take a further quotient by a symmetry group. I think it's perfectly natural. But yeah.
Okay. So one advantage is that we have constructions of exceptional Milverton orbits, and you can find relationships between Milverton orbits and other Milverton orbits, or between slotted slices. And a fibrous slices. And I'll go through plenty of examples to demonstrate the algorithm and the kinds of results. Okay. So let's just cut to the chase. We will be working with unitary quivers. So all of the gauge groups we have will be unitary. And furthermore, just for simplicity, I'm going to work with unframed, so there will be no flavor notes. So the main character of this story is the SUN quotient for that. And it takes the following form. 1, 2, minus 1, and n minus 1, 2, 1. So this is the thing we will be subtracting from other quivers in order to do this subtraction process. Okay. So this is very different to the normal quiver subtraction, which does tells you about Kumaran transitions. So this is just a new tool that we have. Okay. In the paper, we have plenty of rules, and I don't think it's very useful to go through all of them right now, and we'll take more of a
By the way, I guess the quiver subtraction we know is goes beyond just the Kumaran transitions, right? It works very well for the unitary quivers, right?
yeah,
in
unitary
general.
quivers in general.
And if you want to go beyond unity quivers, we had some trouble. I think
That's
it was a bit,
beyond
in progress, yes.
it's a bit harder. But,
Yeah.
Lorenzo was telling us about his decay of fission. There are ways to get the stratification of a Coulomb branch.
Unfortunately, I didn't get to understand all of that, so have to be filled in on it, but yeah. Yeah, but
Okay.
anyway, I think that for the Coulomb branch unitary quiver, I still personally don't know everything about this subtraction, but you told us some things about it.
Yeah. Okay, so this is the SUN quotient quiver, because what it does is it takes some Coulomb branch and forms hypercane quotient with respect to some SUN action. Okay, that's what is SUN. Okay.
And isn't there a reason for this? Isn't it that you can use this quiver to form the group actually, or something like that?
There's the class S thing. So,
the class S, yeah.
Yeah, so for those of you who know about class S, this is the same thing as on a cylinder. Class S theory. Also, the Coulomb branch of this thing is T star. So
Right. That's what I
that's
thought.
according to work by Rodolewski, also Tochikawa, Beninishi. So many people have come across this with this is just okay.
Yeah, I was thinking of this second fact that the Coulomb branch is T star SL, and is there a relationship between that and this fact? Could you get it? Is also a class S theory cylinder?
Yeah, because you now mark to some problem of gluing the surfaces. You could talk about that.
Yeah, okay.
So what's the relationship of this quiver to the class S theory on a cylinder?
Sure. So whenever you have so this is my unit surface, and in general, it can have any genus,
Right.
and you can have any number of points. These punctures are labeled by Newton orbits of some algebra, ADE. In this case, it will be A type. Punctures.
They'll put in orbit closures, I guess.
Yes. So in particular, there's a partition associated with each puncture. Now, from this partition, you can read off, we call it a magnetic quiver. So you can get to a magnetic quiver. which consists of the central node of UN, which I'll just denote by circle with M. And there is some star-shaped quiver which comes up,
Right.
and all of these legs are associated to the different functions. So you get some star-shaped quiver. Star-shaped.
By the way, I think it's true that you can, if you think of these punctures as specifying the monodromy, then if you use what's called a multiplicative quiver variety of this, then you will get the moduli space of local systems with those monodromies on this surface. I don't know if this is related.
I guess this is related to the Seibert-Wilton curve.
Maybe, I don't know what the Seibert-Wilton curve is.
The Travis was saying that there is some monodromy associated to each function, and this tells you about some kind of local description.
Yeah, so I'm saying what I'm saying is you could these labels you can think about. One way to think about them is as specifying monodromy around the puncture for a local system, and then you get a moduli space of local systems with that of rank n, and then actually this moduli space is more or less the multiplicative quiver variety of this quiver.
Let's see, so this is some leaching system? Or what is it for?
No, not simpler. It's just I'm just looking at the moduli space of all local systems on the surface. So all if you like a vector bundle of rank n with a flat connection, such that the monodromy around punctures is given by these labels. Yeah, it's related, I guess, to Hitchin system, but this is simpler.
Simple.
I see. So it is related to the Seibert-Wilton. So it is related to the Seibert-Wilton.
Not sure. So when you say local system, you mean some vector bundle?
A local system, you can think of it as a vector bundle with a flat connection. There's different ways of thinking about local systems. There's like the topological way, which is really topological is really a representation of fundamental group, but there's an equivalence, at least analytically, with this the RAM, what's called the RAM picture. This is related to what Dennis was saying in his talk about Betti versus the RAM. So the Betti picture would be representation of fundamental group, but the RAM picture would be connections, flat connections on vector bundle of rank n with those monodromy. Analytically, these are the same, but not algebraically. But in any case, that's the relationship between the quiver, a direct relationship between the quiver and the surface with labels. But I know you have another relationship you were about to tell us. You're saying that the magnetic quiver.
Sure.
Yeah. The electric quiver is the type. There's no electric quiver here. That you have the type S theory, and it has a magnetic quiver, which is this thing, which is this star-shaped thing. And what makes this a magnetic quiver is because if you take the Coulomb branch of the type S theory, you get the Higgs branch of the magnetic quiver, or
the
other way around. Yeah.
So the Coulomb branch of this star-shaped quiver is the same as the Higgs branch of this four-dimensional theory.
Right.
So this is in 4D.
Usually it's Coulomb branch of magnetic quiver is Higgs branch of electric quiver.
Yeah, that's it. That's right.
Higgs branch of magnetic is Higgs of the class S, but this is a 4D theory.
That's the 4D.
Yeah, so I have the opposite relationship then. This what I'm calling multiplicative quiver variety is a variant on the Higgs branch of this quiver. So if you have a modification of Higgs branch of this quiver, this the main multiplicative version, then you get this moduli of local systems of the surface. I guess you could think of this as some moduli space associated to the surface.
This moduli space of local systems is a simple singularity.
Yeah. Yeah, if you specify the data, the punctures, yes.
Well, maybe we should look at simple examples and get some conclusion.
Yeah. Well, we should maybe discuss this after the talk, because I'm going to derail Guhesh talk completely. But
It's an interesting one. Actually, I've been thinking about things like
I mentioned
the Higgs branch of the magnetic field, what that means in physics.
Ah.
So yeah.
I mentioned this also in Illumini, sorry, yeah, but anyway, the other thing I wanted to say was, so what's the relationship between this T star SLN and this, this magnetic quiver picture?
Blue.
So
It's because the Higgs branch of this associated class S theory is going to be T star SLN for some reason, is that it?
This is the cylinder, and you have the glue on surfaces.
Ah,
If you glue a cylinder to any given surface,
just
it becomes the same.
yeah. So
so then that's a proof that it has to be T star SLN, is that what you're saying?
how do you have in mind this picture?
Because the gluing is taking the product of the two spaces and dividing by the circle. That's
So,
the approach.
This is my
Mhm.
cylinder, and this is the other Riemann surface. And then when I glue, so these x's, for those who don't know, is some puncture. So there is some Riemann surface and there is a puncture. I take these two punctures and join them together. So in maths, this is just I get a quotient. We would say
It's x1 times x2.
Yeah.
Divided after the quotient by the.
So this has associated Higgs branch x1. This is x2. Then I can glue them. By gluing, I just remove these two punctures and join these surfaces.
And for the class S theory, we specify the n, because for every n, we have a class S theory for that particular value of n. And then if you have a punctured surface, at every puncture, you'll have a SLN Hamiltonian action. You can take quotient by. Yes.
Which n? And this is.
Yeah. The SLN or the AN minus one.
So for
It's like the kind of fusion operation here.
that's the equation which gives you have this kind of thing. So if you take a space and multiply by this star divided by the underlying sum, it's supposed to be the same thing.
Yeah. So in case the x1 is then you just get the same thing back. So this is this Euler process. So all of that was to motivate why this question quiver is supposed to do some. The question.
So I can understand that from the class as point of view that thinking of a group will correspond to the gluing. But I didn't see why the gluing operation should correspond to the subtraction.
Yeah, this is the point where we say we are inspired by operations in class S. In the same way that we look at magnetic quivers, we study really different systems, so 6D or 5D or whatever it is. We learn some general lesson from this, from which we're able to come up with something in 3D to help with magnetic quivers.
This glue operation can be interpreted in terms of quotients.
Yes.
Okay. Does it make sense if I say that if you have two varieties given by two quivers, you glue in some sense to some nodes and you quotient by the group.
Perfect.
Okay.
Yeah, that's exactly it. That's exactly it. So this is a different technique we have. We call it polymerization. This talk won't be about polymerization, but that's a very direct consequence of this kind of picture. So yes, that's right.
What kind of gluing we say? That the gluing process can be like those types of quivers.
Yeah.
And you have two varieties. You keep two nodes like frame maybe.
Right.
And you do that and you quotient.
Yeah.
Yeah. That's another way of doing the question, which is very directly related to this thing. We call it polymerization. So
You call it what?
polymerization.
Polymerization?
Yeah.
Polymers.
Polymerization. But this is not
This is
polymerization.
not, well,
Polymerization is the quiver version of it.
yeah, polymerization is the that's a whole other talk.
For Higgs branches, then.
Yeah, so for Higgs branches in terms of these 4D theories,
Mhm.
On the magnetic quiver, it's on the Coulomb branch.
But I'm still a little confused. Yeah. For example, is there any interval that you will expect the mean or the quotient will correspond to a subtraction?
No. So another way to think about it is that, well, that's not quite true. Perhaps it's not surprising that this thing that we subtract is the same thing as the 7-day process.
Yeah.
But there's no derivation. It's just an inspiration.
Polymerization is, I thought you said it was not what you call this gluing for the Higgs of these 4D theories. I thought that was
So
for
the
the
group of these 40 theories
is not
in the
called.
magnetic quiver is polymerization.
On the magnetic quiver, it's called polymerization. I see.
Yeah.
Okay, and that's related to what Tiziano was saying.
And it's related to what Tiziano was saying. But this operation, I'm glad to tell you,
Okay,
it's different, but it's inspired.
okay, all right, thank you.
I think there was some dimensional elements, very, very sound. So, look at the way the legs are embedded in each other, which is what we mentioned.
This is true. Yes, yes. So from dimensional balance, it's also reasonable.
You can describe the technique.
Yeah, I think it's
Yeah,
clearer
that's-
with
yeah,
a,
that's the
it's
journey.
clearer with a very explicit example.
By the way, we don't have to do it now, but if you take this class S theory and you want to compute its Higgs branch, is there a Hamiltonian reduction description of that? I think you told me about some version of that on the high before. Or is that first different? Remember once you told me how to construct Hamilton reduction using Hamilton reduction, either Higgs or Coulomb branch of some class S theory by putting by forming this graph corresponding to the maybe it's the same as this one, corresponding to it, and then putting some data on the vertices and the edges, right?
Yeah, I think it's fluid. Yeah, you can understand fluid. So you take a puncture from one surface onto another. The geometric operation is to do, we have a new surface. And then in terms of the symplectic similarity, it's this thing, you take the product and you divide by the.
Right, no, but you said that there were, I remember you said that you could take like some vector space modulo group that you could build out of this graph.
You try vertices.
Yeah,
So, you have objects which have valence 3 nodes and edges.
yeah,
Yeah, so this is the A1 version of this.
only works for A1, it doesn't work for
A1,
higher.
yeah.
Okay, all right. Okay, go ahead then.
So, okay, so I'll just take a very familiar example of you, or at least a simple one. So I'm going to say what we do on the Higgs branch of a certain free field line. So let us take this space H8. Okay. Now typically this enjoys an SP8 symmetry. So this has SP8. But I'm going to arrange this SP8 in such a way that I actually see SO8 and SU2. So as a quiver, I'm going to take this thing. And SO8. Now, on the Higgs branch, what this gauging does is turn a square, which is flavor into a circle. The Higgs branch of this is the minimum Newton orbit, closure of the minimum Newton orbit of SO8. So So how do I see this on the Coulomb branch of some other questions? Well, here I take the finite D6 squared. So the Coulomb branch of this is the Higgs branch of this, and the Higgs branch, the Coulomb branch of this is the Higgs branch. So we will say that these are, well, we might say they're mirror or weak dual. Well, actually, no, we'll just say mirror, they're not weak dual. And then I perform the subtraction by SU2. So this is the thing that turns, in the electric theory, turns a flavor into a gauge. Is subtraction. But for SU2, I take this 1, 2, 1 quiver. So that's the, by just plugging n equals 2. And the way I do the subtraction is I take the rank of this node, subtract it from this one, and I ensure that some notion of balance is preserved. So some of you have heard of notion of balance before. So
So is it known that the Higgs branch of this quiver is bigger
The one on the left,
on the right?
on the right, if we take Higgs branch, yes. Sure, I mean, these are Dinkin diagrams.
Finite type, right? So any
Yeah.
finite type would give a trivial.
Yeah, I'll just give you a point, yeah.
So when I do the subtraction, anything that participates in the subtraction, I don't have to do anything, I just subtract the ranks. But anything that doesn't, I need to check if I've lost too many flavors. So this 2 used to see 1, 2, 3, 4 next to it. So when I just subtract the ranks, I get this. So this 2 is this one. And now it sees 3, so I reintroduce 1. So we would call this restoring balance. So now I start with this finite D6 diagram, and now I get the FMD form. So that's the result of this subtraction. And the Coulomb branch of this is the minimal. So what I'm trying to convey here is that this is really the same operation that you would do on the Higgs branch. It's just expressed differently on a Coulomb branch.
Mhm.
So the result we get is that H8 C2 is minimum before, where I choose a very particular embedding this SU2 inside SD8. Is that clear? Or
It's this is the same quiver subtraction rule that you were doing before. You were subtracting the unframed and then adding a balance, a framing to make it balanced. Yeah.
yeah, well, actually, here's the gauge. So here I'm just going to rebalance with the Q1 gauge.
Yeah, but usually the procedure was first you added the framing to make it balanced, right? And then, but then for the next step, you would turn it into unframed again,
That's right.
which would be the same.
Yeah, so yeah, we can do it this way. So
Okay.
there's this fully coding trick that we talked about before, and then you do merge all of those. So so I just sort of jumped ahead. Okay, so that's one example which I don't know. Okay.
I mean, no, I mean, maybe some people know this, but I think you've told it to me before. But yeah, I mean, maybe it's related to one of these examples in the literature. But I mean, I know that I guess I know that this quotient has to give you minimal D4 in the sense that this quiver gives you gives you that. But I wouldn't have thought of it in terms of this subtraction procedure.
So again, this is just a consistency check to make sure that what we're doing is right.
Yeah.
So now I'll tell you about stuff that you cannot do with these branches.
Mhm.
One of those things would be some things to do with exceptional limits and orders. So let me show you how you would take.
By the way, this H, the fact that H8 on the SU2 gives you D4, I guess, minimum D4, I guess this is, can be viewed as a special case of this Procesi
Exactly.
description,
Yeah,
right?
that's it. And so it's literally just that instruction.
Mhm. Okay,
So minimal, the minimal limit order of D6 has the following identical. It just takes the form of the outline D6 diagram with the toolbox that labels as.
Who is the number? We don't go before.
I'm not sure, I would have,
We never remember.
Lindbergh was pretty old now, but he was still in charge of transformation groups or some journal like that, but he's probably all retired now. Yeah. It's but he's no he's passed away 2020, Lindbergh. So he was born in 37 and Kopov not the swimmer, the mathematician.
So
Oh.
this is stuff which.
He's younger. He's still alive. He was born in 46. Popov. He is 9 years younger. Now he's 78. Okay.
Okay. So to do an SU2, you once again find a leg of this quiver, something that just protrudes out. You align a 1-to-1 against it, and then you play the same game. Okay. So 1 minus 1 is 0, so I get nothing. 2 minus 2 is 0, so I get nothing. So that 1 and 2 didn't participate. But this 3 loses 1, so it becomes 2. Then I have 2, and then 1 again. Okay. So now I check whether I have this notion of balance. So this 2 used to see 4. Likewise, this 2 used to see 3 plus 1 is 4. But now it only sees 3, because it sees 2 and 1. So to both of these, I just connect up with a D1. These ones used to see 2 and there's what happened. So I get this new program, which I'm going to rewrite in a slightly nice way.
You're gonna do the Colli-Bovi check.
Yeah, I've kind of already done it, but
I did it already, yeah. You did it. I didn't see it yet.
So at the end of the day, I get this program. It's the same as this one. I've just rewritten it. And it turns out this Kumaran branch is the next to minimal. Is the next to minimal orbit of SL6.
What do we know that the two tools are connected to the same one, or not like two different ones?
Ah, okay. So this is true.
You would be in trouble, wouldn't you, if the
You-
balance was more than 1, right? Then you
So
would have.
if okay, so the reason is this.
balancing it.
Well, the reason is this. So when I do a quotient by SU2, I expect the dimension to reduce by the dimension of SU2, which is 3. Okay. But when I do the subtraction of 1 to 1, in total, I'm removing 4. So I only need to have, I have to reintroduce 1 and only 1.
Okay,
So that's why they have to connect to the same.
but like for any quiver where you remove 1 to 1, you will be able to complete like that?
Yes, yes. So I introduce 1 and then I connect up the remaining nodes in such a way that the balance is preserved.
Okay. All the nodes which are connected to one of the nodes which are subtracted really lose balance. Because the numbers are there, it's always change. Yeah. So each one of them, each one of those connected needs to be rebalanced.
Ah, wait, so,
If there's only one node which is connected.
so there's an imprecision, isn't there, with the saying that the Coulomb branch of this, 1 to 1 is T star SL2, right? Then, because of dimension count.
It's still,
We call it GL2.
It's T star GL2 or GLN in
you
general.
still have to fix it, you want.
That's the procedure we are using. But some people don't do it.
I see.
Some
Okay.
people will add a C star, T star, C star.
Okay.
The difference is T star, C star.
Right, but what do you get for the Coulomb branch? You get T star GLN, or do you get T star SLN cross T star of a C cross, or?
So I guess it depends who you ask. We would say T star SL n, because we always factor out this remaining U1 center of mass, we call it. But other people would call it T star GL.
Is that what it is before you factor it out?
Yeah,
If you
that's
do-
what it is before.
It's T star GLN.
T star GL.
Okay.
Yeah, when you can factor this out, it's SLN. We just used to go this way.
Okay, it's actually T star GLN.
Yeah.
Or I guess you could have probably taken Coulomb branch of a slightly smaller group, but you could so you have the instead of taking the product of general linear groups at all the vertices, you can take the quotient of that by C cross and take Coulomb branch of that, the projective version. Is that the same? So instead of taking Coulomb branch of 1, 2 up to n, then down to 1, you could take Coulomb branch of the same matter, but now for the gauge group, you take quotient of that by the diagonal.
Right,
C
diagonal.
cross.
Yeah, it's
That's the same. This is what you're really doing, I guess.
Even though we don't have a way to
to
test
actually
it,
test it ourselves.
because if you write down the global formula, it's not computable. It's the emergency.
For the projective group.
For this family,
1 to 1 and 1 up to n and up to 1. If you plug this into the manifold formula, you won't get anything, you won't get inverse series like convergence.
the reason is the central node has imbalance minus 2. It's negative imbalance, so we manage with imbalance minus 1, it's still computable. But the numbers below that.
But it's
I mean,
it's related to the fact, it's related to the fact that. It's also related to the fact that this T star SLN is not conical.
Yes. The formula only
And so in
works
order to
for-
get a Hilbert series, you want to have a conical variety. Okay,
Oh, so I'll just rewrite what we found.
otherwise it's not a graded element. So there's
Yes,
no
I
Hilbert
use
series.
the- Or maybe you could invent a new grading.
Well, it's-
Grading for one.
To have a grading, you have to, it's a non-negative grading with one-dimensional part in degree 0, that's equivalent to being a cone. We're not a cone in this case, so that's not possible.
But how would you cure? Do you have a simple way to cure it?
No, I mean, I would say that, I would say simply that for a non-conical variety, it doesn't really make sense to. I mean, you could have a C star action which isn't contracting to a point, so if we're using that, you could write down a grading in the algebra, which But if it's, since it's on a cone, it may have infinite dimensional graded components. But otherwise, yeah, it is what it is. You can take. What often happens is you have symplectic singularities which are not conical, and there's a general conjecture that the formal neighborhood of every point is conical. So you can look at local Hilbert series at every point.
Yeah, so for the reason that we said that the infinitely the components will be divergent.
Right, the infinite dimensional graded components gives you divergence, exactly. Right, okay, perfect.
Say one thing about how I choose this embedding of SU2 inside E6.
It should correspond to what you subtracted.
We should correspond to it. So if I just draw the affine diagram of E6, it looks the same. Now, if I delete a node, then this is some algebra inside V6, and this is precisely A5 and SU2.
I believe this is the method of linking to compute maximum subalgebras.
Yes, so this is that.
Is this what you know?
I should know this, but I don't actually know this method.
Whether it's max for the linking or it's not somebody else.
I think you might be right. We'll check that.
Maybe we would want to.
Well, I think linking is under-recognized. People should cite him more and try to understand his papers.
Are you joking? Are you joking?
Well, no, I mean,
It's certainly not under-recognized.
Maybe not
Maybe
in
his
that side.
papers are under-read, that could be, but his name is thrown around all the time.
side, his way of classifying characteristics of orbits is absolutely key in terms of construction.
Obviously, as a point, number of times people mention the word linking.
It's very large.
And his papers were under.
Maybe under
Everyone knows his labels, but nobody knows his papers.
Maximal subgroups of classical groups, 1952 paper by Dinkin, yes.
Yeah.
So you're right, yes.
And this thing computes the regular subgroups, that is also the irregular ones, which you cannot get by this bias.
So you can see how the subtraction is 1 to 1. We get rid of this SU2, we leave this SU6. So that's why maybe this isn't too surprising, at least in terms of the synergies.
Sorry, so what's the relationship between Dinkin's algorithm and what you just did?
Sure. So here, what I did was I deleted a node to get this SU2 times SU6 maximum subalgebra in V6. Okay.
Mm-hmm.
So what this subtraction is like, it's like deleting this node and getting rid of this SU2. So if I quotient out by this SU2, I just get the SU6 remaining as a symmetry. It's the thing that commutes.
Mm-hmm.
So that's why when I take this minimal V6, which has V6 global symmetry, and I quotient out by the SU2, I get something with SU6 global symmetry.
Mm-hmm.
So this subtraction is similar in spirit to Dinkin's way of finding maximal subalgebra.
But it's based on it.
It's based on it.
Based on it. But what we end up with is we end up identifying the orbits of A5 we end up with. Whereas the DQ method just says it's something and something in A5.
Something in here.
So your point is that this is so mathematically what you're saying is we have an embedding of SU2 into something, and now if we take quotient by SU2, we're going to have the commutator of the centralizer of this SU2 acting by symmetries. And now you're going to look at the situations where that centralizer product with SU2, which is a subgroup, is a maximal subgroup.
Yes.
And so then it's covered by Dinkin's algorithm. You could look at other embeddings of SU2 where the centralizer cross with SU2 would not be a maximal subgroup anymore. Actually, sorry, the SU2 cross SU6 itself is the whole centralizer, so that's the maximal subgroup. But you could have some embeddings of SU2 whose centralizer is not a maximal subgroup, and you're interested in the ones where the centralizer is maximal.
But in fact, that's just the one that. So we all out this subject.
Well, but this relates to your previous one about computing the quotient. Not necessarily subtraction.
Not necessarily the subtractions. Yeah, so this would be like the generalizations that we're doing about we were doing.
But even if you don't have the quotient description, it could still be a computation.
Yeah, of course.
You could take other embeddings. Would the subtraction still work if you took embeddings whose centralizer is not maximal?
No. Subtraction
No.
would work, but I guess there are other methods.
Well, what I was making is what, without reference to diagrams,
Mm-hmm.
you could still do the embedding.
Yeah.
Right, of course. Yeah.
Given the symmetry and maximum algebra, you could make a embedding and then they have the same quotient with one with respect to one of the factors.
That's true, yes.
That's just a computation.
That's fine. It's just you get this nice diagrammatic interpretation of the result when it's possible.
But in general, given a subgroup of this group, in this case, E6, whatever, we can always say quotient by it, and we get an action of centralizer on the quotient. This is always true. And you can compute this, I guess, but when in the case when the centralizer is maximal, you get a diagrammatic interpretation.
And so that's what, yeah. So we have both.
Okay. All right.
And as long as the model space is conical, before and after, we are able to test the computation.
Okay. Presumably using these latest methods, such as what we heard from Ben, we can do it in a different way.
Extend it to.
Yes, probably.
It's not a code.
Probably, yeah.
The power for us though. Okay, so this was a relationship between an exceptional note closure and the classical one. So I'll show you one where we have two exceptional note orbits related to each other.
Mhm.
So we'll jump up to E8. We'll do SU2 again since it's good. Okay, so much like the E6, we just take the affine dating diagram of E8. I identify my leg 121 against this thing. Note that you can only subtract these things from legs which are increasing from one up to something. Can't do it. You can't subtract from here, for example, only from a small leg. That's the rule.
Sorry, so you can only subtract on the left, is that what you're saying?
Yeah, you can only subtract.
Because otherwise your centralizer won't be maximal.
Okay, so 1 minus 1 is 0, 2 minus 2 is 0. Then we have 3 minus 1, which is 2. Then 4, 5, 6, 2, 3. Now, then 4 is the only last balance because it's next to 3. It wasn't. So it is a flavor, which I'll just put on the gauge. So now we have to, and this is the result. So, okay, when you apply the manifold formula to this, find that the floor branch is the next to minimum. What we said. Okay. So we find. Then there is no fixed branch instruction that we know of that. This is something that's, you can only find really from this algorithm.
So the only evidence I have is from the term. That's the reason I mentioned the problem. They knew this.
They knew that you got next to minimal E7 this way.
Who knows in which
Yeah.
Well, you have a magical technique for figuring it out, I guess, right? Like, except that in order for you to figure it out, you have to know also that the Coulomb branch of this quiver happens to be next to minimal of E7. Right? You could go either way. Like if you already knew Windberg and Popov, you could use that to guess that this would be that. But you're already very good at computing and guessing what Coulomb branches of certain quivers are, I guess.
Yeah, as long as these are lower orbits. For lower orbits, there are unitary quivers.
But how do you discover them? So for the minimal one, I guess it's clear, right? Because those are just the extended Dinkin diagram. But for the next, the minimal, how did you discover originally these quivers?
Well, there's something about thinking characteristic about these labels.
Yeah.
They'll use different labels to label the SU2 embedding associated with an ordered orbit. And each one of those characteristics can be related to given a height according to which node it attaches to the June boxes or the boxes number. And then depending on the height of that characteristic, it will tell you whether or not a model will evaluate to the diagram formed from the information characteristic and the label associated with it. So that's a vision now.
So you're saying that given a nil quotient orbit closure,
Every node to do it has
you get a certain
you assign
character.
a height to the characteristic.
Those, how do you
Height
call
of
those?
the characteristic is 2. And that would be a square with
How do you call those numbers? 0, 1, and 2?
I forgot,
Yes.
but to give a nil point orbit, they're classified by some Dinkin labels, these 1, 0, 1, or 2, right?
Equals to calculation. We need to make it.
We said that you need to mention Dinkin more.
Well, I think you may call it a characteristic.
So
So given an orbit.
you have these labels,
labels. Now you declare them to be framing nodes,
mhm,
0, 1, or 2.
you declare them to be the framing, yeah.
On the corresponding algebra, right? You take the algebra, you frame it by the characteristics.
Yeah.
You make sure that the gauge nodes are balanced.
Yeah, right.
The construction.
That's the way to go. But
And
only
then the resulting quiver is a Coulomb branch, which is the closure of this node.
And this always works whenever you can,
Only for height.
only for height, what?
Height 2. 2 or less. Do you know the notion of height 2? For orbits?
That means the total number of the labels that adds up to at most 2, or?
Yeah, well, you need to take, to weigh them by the.
This is the quality of the positors or the dual positors.
The Cox-
And
This is a definition by Panishef.
Mm-hmm.
But Dinkin used the concept of height. I think Panishef basically.
See,
So if the sum of these Dinkin labels is at most 2, then you're saying that the resulting quiver really does give you the null point orbit closure in every example you know. And so in this case, it's just,
So you just go with the one.
in this case, it's just the one at that vertex second from the left. That's the one that you use to, those will give you these next to minimal things like you had over here.
The minimal, that's one of the results. Maybe you find it in the book of the Kumaran. The minimal orbit always has the Dinkin labels 1 in the algebra.
Right.
No, the joint is the example.
Okay,
I said that,
yeah.
Yeah.
I think the most striking thing is the A type. Because the joint is made of two, which is so you put so the joint representation of A type has label here, label here,
Right.
the two ends.
Right. Yeah. So the adjoint is one and one, right?
Yeah, so you frame those two. And this indeed is known to be the Kumaran is known to be the
Right. Okay. Perfect.
so E7 has 3 or 4 cases, E8 has 3 or 4 cases. E6 maybe has 2 cases. And you just go over, so F4, you have all the algebras, you go one by one. And you go over all those which are F2,
Mhm.
and all of them have this property.
It's a lot to probably, I don't know how many nilpotent orbits you have of height at most too, but it's a lot of them, right? It's not just the minimal and next to minimal.
Yeah.
There's quite a few. And it works for all of them. You have to prove, you have to verify it individually, or there's some proof.
Yes. Well, if they were not proof, but
Yeah,
just compute.
but you verify each one.
Yes. Yeah, this is the work which was done by
You use it.
I'll tell you.
Okay. How many such orbits are there?
Well, for most of the low rank group is maybe 2, 3. But if you have a high rank, it's inflected. Results straight on to. Because if you think of the thinking diagram, you can attach the two boxes of labels, 1s and 2s, and you can attach a single 1 to quite a lot of to any one of the 2s to stay within the height.
Okay,
Yeah, for A type, it's a fun because you could increase the rank as much as you want, and then
right, but for each group, we're also saying that there's usually only 2 or 3, except for the symplectic groups, you say.
Well, we can do that with the diagrams. Is that actually with the A's as well? Yes.
the subjective is just the volume of the area.
Right,
It's the same number, and maybe factor 2.
okay. But not, the orthogonal doesn't have many, also has many. All the classical.
Yeah, roughly, yeah, you could, for classical algebras, height 2 translates to V%C of the V2. So you take a matrix in the corresponding algebra.
Mhm.
The condition is that the square of this matrix is 0. And now you look for the possibility.
That's this height condition corresponds to square is 0.
Yeah, it's so happening to use the geometry.
Oh, okay, that's interesting. And then the exceptional ones, you just have some small list, but the classical ones, you're looking at nilpotent orbits.
Yeah,
Where-
so you could estimate, say, you know, if you have a matrix of dimensions n, square means that the rank is n over 2.
At
So you
most.
look at all of the integers we
Yeah,
have. So all the number, it's order n over 2 cases.
All right. Perfect.
Now for orthogonal, there is another factor too, because the rank must be even. So you exclude all of the odd cases. So for orthogonal cases, you have everything.
I
If you
see.
think of it in terms of the rank, it's back to rank cases that are.
If you think about it in terms of the rank, it's rank over 2. You're saying.
Yeah, I mean, but those are simple.
But that would be the same thing for a symplectic, actually. It's just what you're defining n to be. Okay.
Yeah, those are very simple linear algebra. It's not usually called, it's linear algebra manipulation.
Okay, yeah, good. All right. Okay, perfect. Yeah, so you can continue if you want.
Yeah.
At some point we'll have to get lunch, but that's since we interrupted you a lot, right?
Okay, there's one feature of the rules which I haven't introduced to you yet, which I want to because it's quite a convenient thing. So let me introduce one term. I will call it a junction. So let's just take this outline basics for resonance. So this node of 3 is a junction. Because it is connected to more than 2 gauge nodes.
Mm-hmm.
And the rule is that when I do a subtraction, my quotient quiver can only go one node past the junction. It can only go. So for example, if I took this E6 and I wanted to subtract the SU3 quotient quiver, which looks like 1, 2, 3, 2, 1. You can see that I have 1, 2, 3, and now the 2 and the 1, well, it goes 2 nodes past the junction, not 1, so I can't do this. That's just the rule. Yeah. Okay.
Okay.
But if you can just go 1 node past the junction, then actually I'll just show you. So this is where the diagrammatic part of this operation becomes useful, and the input series computations become hard. So let me take the E7, it's the only E I haven't drawn yet. So I'll take my 1, 2, 3, 2, 1. So 1, 2, 3, 2. And now because I've only got 1 node past the junction, I have a choice. Can I align the remaining 1 with this 2 or with this 3? So let's take each in turn. Let's first go across. And then we'll go. So those are the 2 possible alignments I can have with this SU3, right? Because it goes 1 node past the junction, and I can choose either node here or here as the endpoint.
Mm-hmm.
Okay, and both of them will give me different results. So let's see what they do. So when I do this one, these 1, 2, 3 gets killed. This 4 loses 2. This is the 2 on the top. This 4 loses 2. And this 3 loses 1. Okay. So this 2 and this 2 are the same, and it wants to see 4 and it sees 2. Okay. So I will connect it with 2 lines to this extra 1 that I had to restore the balance. And this 2 over here wanted to see 4, but it only sees 3. So I connect it back up. So this is why we have one that you reintroduce, and you can always restore the balance by connecting the nodes to this one. So this is one possibility. And if I evaluate the match, actually, it turned out to be the closure of the 5 to hold it, the partition 3, 1, 2. Okay. Now, if I take the other alignment, then this 2 loses 1 and becomes 1, and this 4 loses 2 and becomes 2. Okay, and then I have 3 to 1. The only thing that needs to be evenly balanced is this 3, and it needs to see 2 1. So I just use a 1. And then I just put 2 lines to restore the balance. And if you allow me, I'm just going to make the slide run a little bit myself by redrawing this way. Okay. And the plural branch of this is MTQ. So I have these 2 different results from the subtraction. So how do I choose? The answer is I become greedy and I don't choose. I choose both. The way I do that is by taking the union of both of these.
It's one square.
4 squared.
The problem is to move one step to the leading one, it's not the middle one, it's the one. The next one.
Four 1 squared is transpose is 3 1 2.
So maybe you buy.
Yeah, I mean this one. Yeah,
So I
so we're getting these 2 modulations. That's the result. Now for us, if we wanted to do what we were saying before, and a Hilbert series and I have this embedding and I form the quotient, in general, it's very difficult to find, to decompose these unions into their constituent codes. But with the subtraction, the pieces just fall out. So identifying unions of codes for us is generally quite a challenging thing. So it's convenient that this subtraction gives you that for free.
Is yeah, I would have thought originally that the two different ways of subtracting correspond to different embeddings. I guess the embedding only depends on that central node, I guess. So is that it? Well, for SU3, it depends on two nodes, I guess, right?
Yeah, so here I would say if you take
So it's actually you have 5 in there, but there's actually only 2 nodes which are specifying the embedding of SU3, right?
yeah, it corresponds to this one.
Yeah, the method of linking will give you the
See it from there.
But for no, it's SU3, not SU2. For SU2, it will be just a single node. For SU3, you need 2 nodes. Right?
Yeah. So those are those.
those you
Those two, right? Yeah.
symbolize
Right. So it's always at the end you want it to be. Yeah. So your SU2 is at the end. Yeah, okay. SU3 is at the end. Okay. Yeah. So this is the embedding of SU3, and then centralizer is this SU3 cross SU6 or U whatever SU6. Yeah. Okay. Very well. Actually, it's probably
Yeah.
it's probably yeah. We should get lunch.
This is actually the last example.
There might have been some mistake though, right? Because it's not. Isn't it not SU2 cross SU6, but also with an extra chorus or something? Isn't it going to be like U2 cross? Isn't it going to be like U2 cross U S of U for here? Like if we have these 2 and these 5, instead of getting SU.
SU2 it's D6.
Yeah, for SU2.
Right, but instead of getting SU3 cross SU6, are we supposed to get like U3 cross U6 and take the S of that? Or
Because
something?
the rank would match up either.
Yeah.
So U2, if it was U2 and U6, the U2 is rank 2 and U6 is rank 6, that's like a total, right?
The rank should be 1 less.
So, well, the rank is preserved actually, it's still preserved. So A2 and A5, right? So it's A7, it's 7 total, right? So these Dinkins
Right.
embeddings, so you amputate or delete a node, preserves the rank.
Oh, because you delete it from the affine diagram.
Which makes sense because it's the maximal.
Okay, it's SU3 plus SU6.
You might just want to add the quiver with the intersection of 2.
Oh, yeah. Yeah, so, okay. So
The maximal subgroup of E7. Okay.
Yeah, SU3 times SU6.
Yeah, SU3 cross SU6 will be the maximal subgroup. Okay. Right. Right. Okay. Yeah. Fine. Very good.
These two quickly have an intersection, so if you look at the has a diagram for and A5.
Okay.
So this is not all of it, it's just a small part. For an A1 transition here. A1 cubed.
Right.
And the 2 cubed into this one, which is 2 1 to the
2 squared 1
4, yeah. Which is this one.
2 squared 1 squared.
2 squared 1 squared, yes.
Yes.
This is what the intersection between these 2 points, which is corresponding to this one. Okay,
So, it's worth commenting that the junction rule, seems to correspond in some way to this. That you have these branching A1s. Here in these units, quivers, that you
it
can't.
doesn't always have to be an A1, it can just be any intersection, but it typically tends to be an A1.
But how did you compute this intersection? You just intersected the quivers or something?
So here I do
That's a
the
correct.
Krupp-Pachesi subtraction.
Ah,
Oh, the Krupp-Pachesi subtraction. Here, I identify a U1 slice by
mhm.
having this thing, so. And that gives me, I do that subtraction here, then I'll get this thing, and if I do the same subtraction here, I'll get this thing. That's how we would compute it, but it's also just not documented, so
It's just the orbit contained
that's right.
in both the intersection of the closures.
Large slope.
The intersection of the closures, okay.
Oh, so
But anyway, so all I wanted to say was you get this where did the junction rule come into this calculation?
So the junction rule was saying that you can only go one node past the junction.
Mhm.
And here we have precisely this case, because this one can either go end on this two or end on this three.
Oh,
So now there's this choice. So when this one ends on this three, I get this one. When I end it on the two, I get this one.
but you're forced in this case to only go one past the junction because
Yeah.
you're starting from the left anyway.
Yeah. So that's my.
But you're saying that if you were in a situation where you started from the left and you wanted to go past more than one, then your procedure wouldn't work, is what you're saying.
Just
Okay,
consider those. And then the way you're supposed to interpret these two different alignments is that you find the result is just the union of both of these possibilities.
in other words, okay, so you're always quotienting by this one to n down to one, and you're starting from the left, and you're saying that that the node can, if it includes a node, it's either the last one or the one before it, nothing.
Yeah.
None of the other
that
ones,
one right at the end can only go one node past junction.
Yeah, the
So that
node
two has to end on the junction, and that's it.
node could only occur at the far right or next to right of the thing you're subtracting, yeah. Okay. So the two are the one, in other words. Of this quiver one up to n. Okay. Yeah, so we better get lunch. Let's thank Guhesh. Right, so we can all get lunch, and then we have the room until 2, so you can leave from here if you like. No, 1, sorry, until 1. Saying the wrong thing. We have the room until 1, and then we can move.